Talked about perpendicular bisectors in 5.2. Somebody remind me, what did a perpendicular bisect actually bisect?
A line.
It bisected a line or a segment, right? Not really a line, because essentially a line is what?
Never ending.
Never ending. Okay, so it's really hard to bisect a line. But you bisected a segment, right? Okay, so yesterday you bisected a segment. Today we're going to talk about angle bisectors. So we're going to bisect angles. Tell me what an angle bisector is again. A bisector that bisects an angle, yes. But what does that mean?
A line that
goes from the vertex to the angle.
Okay, good. I heard a lot of the right answers. A line that goes through, or a ray, or a segment that goes through the vertex of an angle and then splits it into two angles. So essentially right here, if you had angle ABD, it is being bisected by ray, line, segment, whatever, BC, right? Okay, so with that being said, because it's an angle bisector, that means that angles ABC and CBD should be what? Congruent, right? Something like this right here. Okay, which you can't see because there you go. Something like that where they're both 26 degrees. Now, we have a new theorem here, and that's not the angle bisector theorem, so make sure you didn't tune out right there. The angle bisector theorem is a new one that states that any point on the angle bisector, okay, again, this is the angle bisector right here. So any point on the angle bisector is equidistant, okay, from two sides of the angle. Okay? Go ahead and take a second to write that down so I can kind of go into more detail about what that means. Okay, so it says any point on the angle bisector is equidistant from the two sides of the angle. This equidistant means that it's going to be the same here as it is here. But remember, okay, and here's what I don't want to leave you in the dark about. We get these perpendicular angles because if you remember in chapter 3 said any distance from a point to a line. To find the distance from a point to a line, you had to have what? Chapter 3, I know I had to go back 2 chapters now. In order to find a point, distance from a point to a line, you had to find that by doing what? I know it's distance, but here's the deal. Why would I not consider this point from here to here the distance between these two lines? Yeah, it's got to be perpendicular, right? The key is the distance from a point to a line must be a perpendicular segment, right? Okay, so it has to be this right here. So what this is saying is, this theorem is saying that when I find the appropriate distance, obviously, this is going to be congruent to this, okay? Something like this. AC is equal to 3m, and CD is equal to 3 centimeters. That's a 3m, 3 centimeters. Now, let's take a second to prove this, okay? If you want to prove this angle bisector theorem, it's not that hard to do. Okay? We created this perpendicular, right? So we created this perpendicular. So we know these two angles are congruent what? Right angle theorem, which says all right angles are congruent. Okay? We're dealing with the perpendicular bisector, so we know that these two angles are what? Congruent. Okay? And we know that BC is congruent because why? Reflexes. Are the triangles congruent? Yes, because why? No, it can't be hypotenuse leg. You guys are getting that confused. We'll talk about that in a second. Okay, angle, side, right? Angle, side. Okay, little quick pause on this information. Let's talk about hypotenuse leg, because a lot of people didn't miss that on the test. Hypotenuse leg means that you have the hypotenuse and a leg congruent. So here the hypotenuse is congruent, right? But one other leg is congruent, because we're proving this right now, is what we're trying to prove. Okay, so right now we don't know this is the case. So we don't have any other leg congruent right now. But a lot of people did that. A lot of people saw angle, angle, side as hypotenuse leg, but that's not, you have to have an actual leg. You can't just have one side. Okay? So it's angle here, and this angle here, and this angle here, and then this because of reflexive, that is your angle, angle, side, proving that triangle be congruent. Now, we know these are congruent. Before this, we know these are congruent because CP, CPC, right? So now, this does prove the fact that angle bisector theorem does work. Okay? So now, instead of having to prove the triangles and all that, whenever we use this, we can just say, oh, that works because of the angle bisector theorem. So we don't have to go through and prove the whole triangle and all that. Okay? Everybody good with that? See. Bueno, let's move forward. Okay. We got to keep in mind a couple different things here. We've already talked about this. An angle bisector divides an angle into two congruent angles. We said in the last thing the ray BC was a bisector of ABD. And the distance from a point to a line is always a perpendicular segment. That's what we're talking about. That comes from chapter 3. Take that. All right. Now, using what we just learned from these theorems and whatnot, let's apply that down here. And we're not going to worry about a thing. Okay? What can you conclude by looking at this diagram on the left here?
5x equal to 6x minus 5.
5x is equal to 6x minus 5. In order for that to be true, what must this be? Angle bisector. How do I know that this is an angle bisector? Because you have your 27s. And how do I know that this is actually the appropriate distance? Because of the right angle or the perpendicular segment, right? Okay, good. So I do know that 5x is equal to 6x minus 5, so I can set them equal to each other if I so choose, and solve for x. What about the right diagram? What conclusions can I draw from that?
4x equals 3x plus 5. Or 4x minus 6 equals 3x.
Yeah, these degree measures, 4x minus 6 degrees, is equal to 3x plus 5 degrees. Again, in order for that to be true, I need to have what? An angle bisector. Okay, how do I know this is an angle bisector?
Because the two things are equal to each other. The two.
Okay, you have the two. Now you have the two segments here congruent to each other with your perpendicular segments. Okay, which is basically the converse, right? Here is the one way. Here's the converse of that way. So it's going to force the angles to be congruent now. Okay, and if you want, you set them equal to each other and solve for x. Okay, has everybody got that? That wants it? Okay. Now, yesterday we learned about a point of concurrency. We also learned about a circumcenter. Now we're going to learn about an incenter. An incenter is a point of concurrency of an angle bisector and is equidistant from the sides of the triangle. Okay, so essentially what we're doing is this. We're finding a point where all three lines intersect, right? Because when their lines are concurrent, that means three or more lines intersect at the same point. But we're going from the angle bisector now. So we're going from the vertices, and we're drawing lines out of the vertices to create point E. So that is our point E is our in-center. Okay? And the in-center, okay, is equidistant from the sides of the triangle. So here we have the distance of a point to a line. Remember, these also have to be perpendicular. That's why I'm drawing these extra lines to show the distance. These have to be perpendicular, and all of these segments are going to be the same because they're equidistant. This varies a little bit, or quite a bit, from the circumcenter, because yesterday the circumcenter could be in the triangle. It could have been on the triangle, right? Sometimes maybe it's outside the triangle, maybe, okay? But the in-center is always going to be in the center of the, or inside the triangle. Sorry, not in the center, inside the triangle. Okay? Okay, these EF, EG, and EH is the distance line because it's creating the perpendicular. And this is creating the perpendicular. That's how I'm measuring my distance. Okay, good question. Now the in-center is a center of a circle that can be inscribed in the triangle. Yesterday we used the circumcenter to circumscribe. That means put the circle around the triangle. Now we're inscribing that, meaning that we are putting it inside the circle. So essentially the distance from the in-center to the edge of the circle is what now? What is that considered? What's that called? The distance from the center of the circle to the edge of the circle.
Radius.
Radius, right? Sorry, I meant to say the center, the in-center to the edge of the circle. But the radius, yes. And if you look closely, you have a whole bunch of right triangles. Here's your right triangle. Here's your right triangle. Here's your right triangle. Here's one. Here's one. Here's one. Here's a little bitty one. Okay, here's one. Here's another one. Okay? It's hard to see that, but if I come down here, that's a little easier to see, right? That's essentially the same thing, just a little different triangle. So if I want to solve this now for x, how would I find that?
Is X on the big part or the small?
X goes right here with this little part.
Is X against the line segment?
Yes, X is the line segment.
Oh,
Sorry. This is X right there. Okay. Now, the easiest way to do this stuff if you're fresh to geometry or new to geometry is to find the length of everything. What do you know this is?
16.
16, right? Because why? It's a bisector, right? This is 16. Here's your right angle. This is a right angle. I know these lines are congruent because they're reflexive. So you have two triangles that are congruent. So this side must be what? 20 because it's CPCTC, right? Okay, so this is 20, 20, 16, 16. What is this?
X.
Okay, it's X. How do you know it's X?
Because that one's X and they're congruent.
That one's X and they're congruent. Why are they congruent?
CPC.
Not CPCTC.
Angle bisector theory.
Because we just said the in-center is equidistant, right? To the sides of the triangle. This is our in-center. Look, here's our lines coming through the vertices. Here's our lines coming through the vertices. That's the in-center.
Oh.
Okay, now how do I find X? Oh, don't let me down. Pythagorean theorem. Very good. Simplifying Pythagorean theorem. So far, you guys have been good. Every class has been doing it pretty quick. Look, you have a right triangle. Just remember that 20 is the length of the hypotenuse because it's the longest one because that's the one across from the right angle. Okay? And that's it. Any questions?